Warm regards, everyone. Today's discussion topic is automated flood potential geospatial model development for management decision support. And two of my students, with my guidance, Bailey and David, they created this research project. This is actually a decision support system project so that it can help your watershed managers or field managers to work on this result. Little bit background. So as an immediate impact of climate change, flooding and flash flooding are normal geohazards in present day America. We are seeing this many times over a year and in a year. These potential rain events can range from having almost no effect on human lives to having truly devastating effects. Nowadays, your flash floods are happening a lot. So these potential disasters can cause damage to private property as well as homes and create life-threatening conditions for local residents. And as planners, mostly not planners, as your managers, so we are kind of accustomed to reactive planning. That means dealing with the consequences after flooding, in this case, when flood recedes. However, proactive planning is essential to mitigate such flooding type your geohazards. And due to climate change, most of the geohazards impact is getting enhanced. So if we go for proactive planning, maybe the severity of the geohazards, its impact may go down. So geospatial technology is one solution towards developing such geospatial vulnerability, susceptibility, probability, potential determination to mitigate the geohazard impacts. Thus, geohazard managers and even stakeholders could take preemptive measures using the proactive planning suggestions so that such hazards cannot create unmanageable damage. So objective is one straight goal we have. The goal of this project was to develop an automated geospatial model for flood potential prediction so that environmental managers and other stakeholders who are kind of dealing with such miseries would be able to take proactive measures for flood mitigation. Study area, we choose the whole county where UNG or the ISA program actually based on, and Hall County is considered as a good scenario for this kind of study because the northern part of Hall County is in the foothills of the Appalachians. It rains a lot in a single county. The southern side, the difference between the northern and southern side precipitation is kind of huge. So that is the reason we choose Hall County as our study area. And the data for this model is like two different type of your precipitation related data we used. One is NOAA, the PFDF's 100-year 24-hour storm event data we used, because nowadays flash floods are happening a lot, and NOAA actually is using the climate change based is updating until for Georgia it is until 2013 already got updated. So climate change based information is embedded to it. We also use the PRISM, it's an acronym, the PRISM program precipitation raster. So that's 30 years of until 2010 raster was available. So we used it. And StatsGo soil data was used because soil is a big feature for analyzing flooding because runoff mostly depends upon the soil characteristics. And next one we used NLCD, that's the National Land Cover data set, the land use land cover information it provides. So that way we know that if it's bare soil, then runoff will be higher, and if it is kind of vegetation, dense vegetation is there, maybe runoff will be less. and also we use Tiger road data. The road data was embedded to the final product, so that way it would help your environmental managers to know if such events happen, whether there is a communication network is there or not. They need to know. So this is about StarsGo data. The soil data is considered the most important in flood potential modeling. And we use the drainage, permeability, hydrologic group, soil texture, slope gradient, and slope length. These are the characteristics used in our study. And it to be noted that we did not use the DEM, digital elevation model, as an independent data, which is very important for flood modeling in this model. Why? Because we got the slope gradient and slope length, which is calculated through your StarsGo, the newest StarsGo and Sorgo and G-Sorgo data. It is available, and slope gradient and slope length will take care of the elevation based analysis to flood potential modeling. And we know that drainage is a major criteria, because the soil, if it doesn't drain well, then waterlogging will happen. If it drains well, then flooding might not happen that well, that much. And we know that permeability is a major factor. Higher the soil permeability, lower the chance of flooding. The same way, soil hydrologic group, like in this case, in our county, ABCD, AYD, BYD, and CYD, these are of varying potential of infiltration. So that is the reason varying potential of runoff. So if runoff is higher, then there is a good chance. Infiltration is lower, there is a good chance of having much flooding. Soil with clay texture is always important. The clay soil, higher potential flooding, and sandy soil with higher porosity have low potential of. So these are some of the examples. Like when we do the model, the very first thing, based on their potential for flooding, we group them into either 2 class or 3 class or 4 classes. You will see later. In this case, the soil drainage was classified into 2 classes. So we put 0 if it is lowest potential or lower potential, that class. We put 1 if that class is higher potential. In our case, excessively drained, somewhat excessively drained, well-drained soil were reclassified as 0, and moderately well-drained, somewhat poorly drained, and poorly drained and very poorly drained classified as high potential as 1. You check that in every space I have or we have the link to the PDF file, which actually the USDA NRCS folks, they already developed, and that information is our input for creating the reclassified rasters. Then hydrology group the same way. It is, you can check that from the slide. They are classified into 3 groups. Lowest one is 0, moderate one is 1, and highest one is 2. And soil texture, similarly, we have 3 classes. Lowest one got the class 0, sandy and loamy. Moderate potential, that's 1. Sandy clay loam, silty loam, silty clay loam. They are classified into moderate potential for flooding. Class, like your reclassified value as 1. The other is 2. And you check that the link for analysis or distance support on this thing is provided. Then soil permeability, the same way we classified into 3 classes based on their potential for flooding. Slope gradient, also exactly same way, but we classified that into 4 groups. So higher the range class is lower potential, and smaller range class means the flat area. So flat area is mostly the higher potential. In such cases, we use Jenks classification algorithm. So that way it classified into 4 classes, and we group your lower potential, the higher range class as 0, and so on and so forth. And the link for this distance support is provided. Slope length, exactly similar way. we have 4 reclassified groups based on their potential. Then the next one is land cover. Land cover is not exactly the figure is not showing the reclassified classes, but actually we had your 3 classes. The lowest potential were for flooding were forest, mostly 41, 42, 43 of the NLCD, the value, and moderate potential were shrubs and herbaceous and pasture and agricultural land, because generally they are kind of in the flatter areas. And higher potentials are your water body itself and your urban, suburban areas and bare soil areas and wetlands. And as we know, for flooding, rainfall or precipitation is one of the most important stuff, I think. So we got the rainfall intensity data from the NOAA PFDS website, and we classified into 2 classes. The lower range classes are our low potential, because if it rains intensity is low, so we will have a lower potential for flooding. If it is high, then higher potential for flooding. And I already explained Hall County in the northern side has northern and southern side has really very varying rainfall and also intensity. The precipitation variation raster was also classified into 2 classes. Similar explanation to the storm intensity event. And the next one is very important. Once we already classified all our input geospatial layers, which can predict the potential of flooding in Hall County or in your area of interest, next thing is to figure out which particular your input geospatial layer is most important for finding out the potential, and someone might be lowest potential. So immediately, as a researcher, we can think maybe precipitation has the highest importance, because if there is no rain, there is no flooding. Maybe we can think, say, if the soil drainage is understood, then we can understand easily where the potential of flooding is higher. So that is the reason person to person, actually professional folks who have expertise in different aspects of environment, they are kind of weight factor varies. So that is the reason there is a method developed called Delphi. This is the most important part of this research. So the Delphi method is known as estimate talk estimate, or ETE method. It is a structure communication technique which originally developed as a systematic interactive forecasting method, which relies on panel of experts' opinion, and experts rank those input layers based on their own thinking and own expertise, and based on their thinking of importance into this particular analysis. So every expert their own ranking, and we actually took all their rankings of the input layers and create a inverse weighted scale for each layer, and use that inverse weighted scale for individual input parameters, multiply them, and at the end use a tool called weighted sum. So weighted sum will take care of individual weight of the individual your inputs, and finally at the end it will provide the potential flooding raster. So this environmental proactive planning decision support modeling, where many geospatial layers are used in this Delphi method, weight distribution holds important. And as I told, this is the key for a sound and efficient result obtaining. So you can see the inverse weighted score we found out, and we assigned these scores to all the input layers. Drainage got the highest, 25%, hydrologic group 7%, soil texture 7%, soil permeability 9%, slope height and slope length got 12.5, 12.5, NLCD got 7%, and you check that both precipitation rasters got 10 and 10, that is like 20% wattage. So this is the final model. You can see we have the our StarsGo data over there, and StarsGo data come as a vector data. So vector data in geospatial modeling or automated geospatial modeling, all the data must be of the same cell size raster. So same cell size raster can overlay on each other, so that in this case we are using say 9 different individual layers. So 9 pixels on each other can be overlaid. So they can be combined as a single pixel, which will provide us the flood potential. So your StarsGo data created your 6 rasters, and we reclassify those rasters based on their potential, which we discussed earlier. The NLCD, rainfall intensity, and the precipitation distribution rasters were reclassified, which we already explained, based on their potential for rainfall intensity, flooding. So now reclassified rasters, all these 9 rasters are multiplied by their weight, the Delphi based weight we already obtained using the weighted sum tool. The final raster is the flood potential raster. You will see in the result. So we also use Tiger Road data, as I explained earlier, to just provide decision support for the planners, or managers, in case the flooding happens. This is the final result of the flood prediction model or potential model. So you can see in the left the flood value range between 0.83, which is dark red, to 7.63. Please do not mind, actually the color coding should be different. So 7.63 should be opposite, then is red, and 0.83 should be green. So higher the value, greater potential of flooding; lower the value, lesser potential of flooding. Hull County is in a better kind of situation. We do not have too much area in the highest range of flooding, but still a few pixels you can see they are very high range of flooding, and most of the county is in the average potential of or moderate potential of flooding. Then you can see we kind of overlaid the road network on it. So that means we are seeing some of the highest potential flooding does not have very much, that is in the bottom middle, so the green areas, so do not have like intense road network. So maybe those area your transportation network should be developed, so that way it can be managed if and when, God forbids, this kind of flooding. And summary and conclusion: we know that geospatial technology and automated geospatial model development hold the key for such complicated environmental issues, which can be solved through proactive management decision support system. Most data used in this analysis incorporate climate change related information. We use the very important Delphi method for making our decision, for making the model, and also we embedded Hull County, the Tiger Road data on this Hull County flood potential raster, so that your flood hazard managers or like environmental managers can mitigate the flood hazard in interactive manner as well as proactive manner. Finally, this model can be replicated and upgraded by any researchers with ease. And thank you. You can contact me, Sudhanshu.panda@ung.edu, if you need help in replicating or upgrading the model for any other geospatial location. And thanks for listening.